In this session, we will complete our discussions on Prim's algorithm by looking into efficient implementation of the same using some good data structures. Recall that the Prim's algorithm has complexity order n square plus m when we were maintaining the weights of the edges of the form xpx, okay, and we are finding the minimum. So first you are finding the minimum among n minus 1 weights, then n minus 2 weights, and so on. But there is a very clever way to reduce that complexity, because you are finding the minimum and then deleting. The natural choice is to use a heap. Okay. If we maintain the minimum edge weight, okay, let RV equal to weight of VPV. VPV is the minimum weight partner. The actual minimum weight is RV. Let for every vertex V, we get these two information, VPV and RV. Therefore, we not only change the partner, we can also change the weight accordingly. So we can maintain this in an array. So RV for V belong to, initially V minus S is almost V, but for one element. V belonging to V may be maintained in an array. In that case, we find the minimum, okay, find minimum of RV such that V belong to V minus S, and then you are moving V out, and then we are doing the delete min. This vertex will not be there at all in the collection. So next time you have to find the minimum among the vertices in V minus S. In that V minus S, V will not be there, because that is, therefore find min RV with delete min, then update RV where V belong to V minus S, delete min and move V to S, update RV where V belong to V minus S. These are the operations that we are doing. So let us write the pseudocode. When we maintain these values in a heap, because delete min can be done in log n time, it can be done in log n time if we maintain the values in a heap. If RV values are maintained in an array, the finding the minimum first requires n minus 1 steps, because V minus S has got n minus 1 element. Then one element is moved, the next step requires n minus 2. You have to find the minimum among the RV. RV values are changed, they are all updated. So again you have to scan the array and find the minimum. But there are only n minus 2 elements. One more element goes away, RVs are updated. Now again you have to find the minimum in the array, that is n minus 3. Alright. So every find min operation is linear. So the total cost becomes quadratic. Suppose I maintain the RV values in a heap. The RV values are maintained in a heap and not in an array. Then delete min can be done in log n time. Finding the minimum, deleting that minimum, they can all be done in log n time. Alright. So here is the pseudocode. But updating R of V is going to take some time that we have to estimate. Alright. Let us see what is actually involved. When we write the pseudocode, it will become clear. Again, A equal to empty, S is some vertex R, V minus S is V minus R. This partition is represented by in S R equal to 1, in S V equal to 0 if V is not equal to R. Okay. And parent of V equal to R if parent of equal if V belongs to adjacency of R and is undefined if V does not belong to adjacency of R. If that is not neighbor, there is no crossing edge, there is no partner information. Okay. And RV equal to weight of VR, that is the only minimum edge, right. This is a partner of V, partner of V, that is weight of VR. If V belongs to adjacency of R equal to infinity otherwise. It is not defined, partner is not defined and its R value is also not defined. Okay. Now make a heap with R value. Let H be a heap containing RV values. We form a heap, okay, heap of these n values. Some of them are infinity, it does not matter, okay. This is a min heap containing the RV values. You can build this heap in order n time or in a naive way in n log n time. Okay. The total cost of building a heap is you can keep inserting and building a heap naive way. There is a clever way to build a heap of n values with in order n time. It is all well known. basic algorithms. Let H be a heap containing RV values. V belong to V minus S. Now, for I equal to 1 to n minus 1, we have to find the minimum V, a vertex V which has got a minimum R value, all right, and okay, let that is from the heap. When you extract min, it removes the min value and puts that in V. So, V equal to extract min of H. Then what you do is that A equal to A union V PV A equal to union V PV. You have added that edge. Now you have to move. So, in S V equal to 1, this is moving of this, and then now comes the crucial step, updating of R of V, updating of R of a vertex in V minus S. Okay. Now we have to update, let us use another notation, update R of Z and P of Z for Z in V minus S. This updating is to be done. We have found out the minimum and we have added the edge, and now we have moved V. Now we have to update. So, what is this updating step consists of? If Z belong to V minus S and Z belong to adjacency of V, this is what you have to check, because Z belong to adjacency of V. If weight of V Z is less than weight of Z P Z, if weight of V Z is, then V is the new partner. Earlier Z has partner P Z, right. Then if this is the case, then P of Z equal to V and R of Z is changed to weight of, R of Z is changed to weight of V Z, because this is a new partner, new minimum partner, and the weight is this one. But how do we do this step? RZ values are in a heap. For example, I may have a heap 40, it's a min heap 70, 60, 80, 93, 68, 121, 100. So you have a heap like this. This is where the values are. Now you have to update R of Z. What is the earlier value of R of Z? Earlier value of R of Z is weight of ZPZ. That's how R is. R will carry always the value, the minimum weight crossing edge from V, from Z. So that is now further reduced because this is smaller value. R of Z is updated to a smaller value. So something like you are maintaining a heap of values, one of the values is reduced. Let us say this 93 is reduced to 40 or 42, or let us say 93 is reduced to 32, just for the sake of. You can't simply leave the value there, it won't be a heap. In order to maintain the heap property, you have to move this up, because in a min heap larger value cannot sit on the top of smaller value. 70 is larger than 32, not valid. So swap 32 here and bring 70 here. 40 cannot sit on the top of 32, swap 32 here and bring 40. This way, when you decrease a particular value in a heap, it may violate the heap order property, and that means it may have to move up, and that may take log n time, because a heap with n items will have height log n, and the value you are decreasing may be at a very low level and it may have to go all the way up. Therefore, the worst case complexity of this update, the worst case complexity of this update is log n per update. Okay. So this update R z equal to W z put in a heap, we call this as decrease key in heap from current R of Z to W V Z. This is the current value, this is the new value. There is a heap and it has got R of Z, but that R of Z must be reduced to W of Vz. So this step implemented in a heap is through decrease key operation in a heap. Decrease key operation in a heap takes order log n time. A decrease key operation takes order log n time. Since it is taking order log n time and there are m updates, okay, the earlier complexity was n minus 1 plus n minus 2 plus 1, and then degree of the first vertex plus degree of second vertex plus degree of last vertex, degree sum. When you implement in a heap, each of them take log n time, therefore it is n log n. Here also each of them will take log n time, therefore the total is degree sum m log n. Therefore, when we implement Prim's algorithm using heap. Thus, if we implement Prim's algorithm by using an array for RV values, the complexity is order n square plus m. If we implement Prim's algorithm by using a heap for RV values, all RV values are maintained in a heap, and you are doing the delete min and you are decreasing certain values in the RV values. Some RV values are reduced. If we implement Prim's algorithm by using a heap for RV values, then the complexity is order n log n plus m log n. Order n log n plus m log n. Well, if you look at sparse graph where m is order n, this is n log n and m log n. Okay. Whereas n square plus m is always n square, m is n, that is okay. So we have two algorithms. One algorithm has a complexity n square plus m. Another algorithm has a complexity n log n plus m log n. When m is order n, this is order n square, whereas this is n is also, this is order n log n. That is, for sparse graph using heap is better. For dense graph, let us say m is order n square. This is order n square. N square plus n square is order n square. But this one is order n square log n, because m is n square log n. So for sparse graph this is better. For dense graph this is better. For dense graph using arrays is better, because if you use heaps you have another log n factor added up to the complexity. So asymptotic complexity is bad, it is worse than n square, right. Therefore for dense graph arrays are better. For sparse graph implementing the RV values using a heap is better. Okay. However, if you use Fibonacci heap, that is where you see the, if you use Fibonacci heap, if we use Fibonacci heaps, n minus 1 extract min has total cost, because amortized cost is log n minus 1 log n is order n log n. Degree sum is order m decrease key has total cost order m, because decrease key is order 1 amortized cost in Fibonacci heap. So if we use Fibonacci heap, the complexity is going to be order n log n plus m. So whether it is a dense graph or sparse graph, this is better than both the implementation. Okay. For dense graph, this is just like the array based one. For sparse graph, it is like the heap. It is taking the best of the both world. Fibonacci heap, right, is kind of combining the best of the both world. It beats the array. For array, dense was earlier better, but for dense this just matches. For sparse graph, it is better than it's n square, whereas this is n log n. Okay. So for sparse graph, it matches the best of the two, and for dense graph it matches again the best of the two. In other words, this gets the best of the two for all cases. Okay. So order n log n plus m is the complexity that we get if we use Fibonacci heaps for Prim's algorithm. This is of course an asymptotic result. There are a lot of practical details that one may have to look into when we consider the implementation aspect, and for moderate sized graphs, a simple array based implementation is satisfactory. Okay. You do get some advantage using the heap, but asymptotically speaking, Fibonacci heap offers the best of the both world. Okay. So with this remarks, I conclude my discussions on Prim's algorithm. Thank you.